All right. We're talking about enzymes, okay? And we're going to talk about inhibition. Now, if we do a experiment and we're going to look at enzymes, you're going to mix a certain amount of enzyme with a certain amount of substrate, and you're going to measure a certain amount of product. Okay, to analyze the data from that experiment, what would we do with that data? How do you look at an enzymatic reaction? You graph it. Oops, all right, let's graph. Okay, here's a graph. You graph what? Two things, right? What are you looking for, ultimately? The what? You have to speak up. My ears are all stopped up. The rate of the reaction. The rate of the reaction is velocity. Velocity is product formation, some amount per time. Okay, so velocity is the production of product, and that's a rate, versus what? Substrate concentration. What would you expect as you put more and more substrate? What should happen to the velocity? Should increase. But it's not linear. Okay? It is in a curve that looks like this. Oops. Ish. Okay? All right. What kind of kinetics is that called? Who developed the equation that mimic that? Michaelis-Menten. Some things that are important. It reaches an asymptote at the end called what? What's the top of this graph? Vmax. Okay. And we can get to something called the rate constant, Km, which is found at what? Mathematically, 1/2 Vmax. When substrate is equal to, when the substrate is equal to the Km, and you substitute it into the equation comes out mathematically to 1/2 of Vmax. Now the substrate concentration can equal anything, can equal 2 Km, can equal 3 Km, can equal 4 Km, can equal 1/2 Km. All right, the math will tell you how much velocity is there, but there's something special about when Km is equal to the substrate concentration. That means the numerical value is equal. Okay, and that's 1/2 Km. All right, this is a enzyme. This is the Michaelis-Menten. Although that's hard to get. Why is that graph hard to get? You got to do a lot of points. You got to do a lot of experimentation. So what we did was we changed the graph to make it look straight line, called the double reciprocal plot. Why is it the double reciprocal plot? We plot 1 over V, 1 over the substrate concentration, and I get a straight line. Right here is a value that is 1 over Vmax, and right here is what? Woo. Stop. Right there is what? Do you remember? It is negative 1 over Km, and I feel like that utter failure as a teacher. All right, those are some interesting things that we need to know. All right, so that's the enzyme working with a substrate by itself. Then we started talking about inhibitors. Small, usually molecules, most of the time drugs, although there are natural inhibitors, that will stop the enzyme. What would be the difference in the graph under Michaelis-Menten if it's inhibited? What would the graph look like now? Vmax wouldn't be as high. So if you inhibit it a little bit, that's an inhibited one. If you inhibit it a lot, what would you see? Nothing happens. Okay? And the first type of inhibitor I talked to you about was an irreversible inhibitor, which means the molecule interacts with the enzyme, becomes covalently linked. Its velocity after that point will be 0. Can never be corrected. It becomes covalently attached in the active site, and effectively that enzyme is dead. For the cell to produce that reaction, it would have to go all the way back to the DNA and create another enzyme for that to function, which takes time. All right, a competitive inhibitor. Competitive inhibitor is kind of interesting. All right, the substrate is going to bind into the enzyme, and you can see that there's a specificity. There's a shape that binds to the substrate. Substrate binds in. The ES complex is important because that is the only way to get the product. Okay. A competitive inhibitor gets into the active site because it is a similar shape. Now, what happens is all of the enzyme is in the mix, right? And the fastest you could ever get is if all enzyme had substrate. But if you throw in an inhibitor, sometimes the inhibitor gets in the way. Okay? If it's in the way, it doesn't produce product. That means it ties up the enzyme and doesn't allow it to do its reaction. What you see overall is a diminished production of product because at any one time, there's only so many ES complexes. There could be some EI complexes with do nothing. At low concentrations of substrate, high concentrations of inhibitor, you can almost get it completely inhibited. Almost no activity. But as you raise the concentration of substrate, you can overwhelm the inhibitor, okay? And you can actually get to the Vmax. Because you just have to, though, give a whole lot more substrate because what you have to do is compete out any inhibitor binding. You do not change fundamentally how the enzyme works. You change how much substrate it takes to get it to the full ES complex. You don't change Vmax. You do change the Km. What is the concentration necessary to get to 50% full? So if I would plot these two using the line Weaver-Burke, what we see is normal. Okay? What we see is inhibited. And what we can see is that the Vmax does not change. I fundamentally do not change how the enzyme works. As long as it gets full of substrate, it will produce product at the rate that it wants. But what you will do is see the Km changed. So here is the Km way over here for the normal, and a Km here for the inhibitor. But I told you that it takes more inhibitor to get to the volume. Remember, this is -1 over the reciprocal. And so this represents a larger value than that does. Okay? And so, if you did an experiment and you didn't know what the inhibitor was, how it behaved, if it has the same Vmax, then it is a competitive inhibitor. The non-competitive inhibitor is a little bit different. The non-competitive inhibitor, the small molecule that is an inhibitor binds to the enzyme, but it does not bind at the active site. All right. What it does is, if you take a look at the first one, enzyme binding, competitive inhibitor and binding, same shape, bind, this just gets in the way. But the active site is optimized for the transition state, which is what it facilitates or lowers the energy barrier. What happens when that non-competitive inhibitor binds? What happens to the active site? It changes its conformation. But that conformation is essential to stabilizing the transition state. So the enzymes become slower because what essentially happens is the transition state becomes higher in energy. And so you fundamentally change. Now, substrate binds. Did I change how substrate bound to the enzyme? No. The same amount of concentration will fill up half the active site as before. But will it go as fast? No, because the actual shape of the enzyme doesn't function as well. So, in this case, we're going to be opposite. The Km for the two cases, a normal and a one that has inhibitor with it, have the same Km for substrate. The same concentration will reach half Vmax. Okay? But because the enzyme does get in the way and slows down or lowers the stability of the transition state, the Vmax will change. All right? And so we said Vmax will change. It should go down. If you take a look at that, that's 1 over Vmax. So that represents a lower number than this. Now, in this case, it's a little bit more complex in how the binding. E can bind to substrate. Before it produces product, I can get in there and kind of mess it up. And so there's multiple bindings. All right. There's what's called a mixed inhibitor. Okay. In this case, if you draw your experiment and you plot it, is it competitive? Well, at this moment in time, most likely if I was the teacher and you were in the lab, I would make you redo it. Okay? Because it doesn't have an intercept at either the Vmax or the Km, which is what I would expect. Did this, usually your experimenting is wrong. Okay? You did something wrong. But if you really look at it, and you really look at it, and it comes here where it is neither a Vmax nor a Km, and you've done it enough to you really feel good and confident about your data, then it could be a mixed inhibitor. Okay? There are rarer cases of these, but they do happen. An uncompetitive inhibitor, okay, is interesting in that it can only bind to, and the binding pocket only exists once substrate is bound. In this case, there is no there's no same Km, there's no same Vmax, but they are all parallel to each other. If you did this and your data came out this way, I could pretty well say, yeah, you've got an uncompetitive inhibitor. Okay, so these are 4 different ways. Now, of the 4, the first 2, non-competitive and competitive, are the 2 most often seen. But I love this because I have 4 graphs, and that makes a really good what? Multiple choice question. Which one is a blank? Okay, and could be a wonderful exam question. Yes?
What are the characteristics of the mixed inhibitor?
They're mixed in terms of it will inhibit, and if you can take a look at this, it does misshapen the active site, lowers its overall Vmax. Okay? But it also competes for the substrate binding. And so it does take more substrate to actually bind to the active site. So it's binding to near the active site and modulating that, and modulating and changing the actual conformation of the transition state. And it's really a much more complex move on the whole enzyme than the other 2. And so it gives both characteristics of the other 2. Usually it is one or the other non-competitive. It's usually the non-competitive or competitive, but there are some examples where it does both. Okay. Way back when we changed the delta G prime or a naught, okay, where we have all of those G-chem things that have delta G's with a 0 standard free energy, there was a little apostrophe for enzymes, and that was a a normal concentration of water, there was magnesium concentration, and there was a pH defined. All right? Because these three things influence enzymes, we standardize and we make sure all of our calculations are based upon a certain pH. The reason is you can do another experiment with enzymes and you can reach Vmax for an enzyme at different pHs. And so, if you take a look at these two enzymes, pepsin and glucose-6-phosphate, can you identify one of these, the actual place in the body where one of these is active? Pepsin's in the stomach. Why is that? The pH optimization, it is most functional at a pH in not just the stomach, but digesting stomach. The pH range or value is maximum. Okay, and sometimes this can give you a clue. Glucose-6-phosphate, where is it in the body? It's in glycolysis, right? It can be part of the gluconeogenesis. But what tissue type would you say that's in? Everything but digesting stomach. Okay, it can be anywhere, and so sometimes this gives us a good clue. Sometimes it could be just general. Okay, every enzyme has a maximal pH value that it works best at. Okay, and for quite frankly, most of them are near the pH of 7.4 normal pH, blood pH. Okay. There are some in the lysozyme that are more acidic bound, some in the stomach that are more acidic bound, but the majority you would assume would be at normal pHs. All right. We are now going to give you a handful of examples of the many, many thousands of enzymes that can work. And remember, we're going to give you some examples to make you look at things. And then you're going to glean clues of principles that happen in enzymes. And so if you have a few principles, you can look at any particular one enzyme and see what's going on. But we need to kind of understand what an enzyme does. And so for enzymes functionality, there's a lot of things that we will want you to know. All right? Usually, we want you to know the enzyme's name. Okay? We want you to know its substrate and its product. Okay. Other things that we need you to understand about enzymes, and a lot of times we will point these out, is a cofactor. There might be something more than just the protein itself that needs to be there for the reaction to occur. Then we will learn regulators. What turns it on? What turns it off? We will want you to understand the sequence of binding. And here's the chemistry of biochemistry. We're going to look at the structures of the intermediates and transition states. That means we're going to be looking at the mechanisms of what happens. Okay, which protons are being deprotonated, which electrons are being nucleophiles, things of that nature. Then we can identify the amino acids that participate, that either stabilize or that actually participate in the actual reaction itself. All right? And sometimes we'll even identify its lysine 462. But a lot of times we won't, because depending upon which isozyme you look at, one human versus a chicken versus whatever, they may be different numbered, but they're very similarly oriented in the overall sequence. So sometimes we give numbers, sometimes we don't. All right, so for any enzyme, these are the list of things you need to know about them if we introduce them. If I don't introduce something, then you don't need to know that about that particular enzyme. I'm going to introduce a whole class of enzymes called serine proteases. All right. What does serine proteases make you think? Let's get some of we can get some information from the name itself. Serine. It's got serine in it, so that must be very important. Okay. Yeah, the protease, ACE is usually breakdown or reaction, and protein, okay, we're going to break down proteins using serine. Ultimately, that's what's going to happen, okay? three major classes or three major examples that we really understand very well, chymotrypsin, trypsin, and elastase, are enzymes that are included in this entire class. All right? They are a digestive enzyme bundle that works in concert to each other, okay, and they hydrolyze peptide bonds. There is a different specificity for each one of them, but they always break down a peptide bond. It's just which bond do they break. And they're very specific about which bond they break. And to break down the steak that you eat at Outback, you have to have all of them. Okay? Chymotrypsin is usually the one that we looked at first. It breaks peptide bonds. In vivo, its specificity is to hydrolyze peptides on the carboxy side, that is after any aromatic bulky side chain. Okay, and so the three aromatics are obviously the ones that you think about, but one that is bulky that you don't think about is methionine. All right, so tryptophan, tyrosine, phenylalanine, and methionine. Now, we do a lot of study with this enzyme because it can hydrolyze ester bonds. And so sometimes we use an organic molecule because it's cheap and it will be broken down and we can study the enzyme rather than looking at the specific substrate, the real substrate. So some of the data that you'll see comes from the production of things from an organic compound being broken down, and some will be from the protein. Here's chymotrypsin itself. All right, and you can see that I identify a handful of residues, all right, that are important. In the space-filling model, okay, you see that right there, and you see this right here? That is the active site. It's kind of buried in there. Can't quite see it. All right, it's still in a cleft or a pocket, and that's how most enzymes work. And then when I do the ribbon structure, what I've done is I have identified some key amino acids using ball and stick, and there are three major amino acids that are in the active site that make the serine reactive. Okay. If you take a look at this, that gives you a little bit of information. This gives you a little bit more, and you can see that pocket's actually a little bit bigger than what it looks like here. There's actually a big channel that runs, and that's the big channel here. Look at the primary sequence. Tell me something that you see in the primary sequence. What do those little numbers mean? What does that 1 mean? Great, first amino acid. What does that 254 mean? It's the 245th amino acids, right? I think I said it wrong, but it's 245th. All right, as you look through this, here is an important amino acid, serine. In this case, it's the 195. There's an aspartate and a histidine. Serine, let's see, the serine, aspartate, and the histidine are right in this area. Those are part of the active site. What else do you see?
There's disulfide bonds.
Yes, that's important. There's disulfide bonds, and they are functional to keep the three-dimensional structure together. What else do you see in that primary sequence? The SR alpha and beta. That's in the secondary sequence, but this primary sequence, what do you see? What number is that? 1, right? What's this? 13. What's that one? Wait a minute. What's wrong with that? Yeah, what happened to 14 and 15? They're gone. It's broken. But look at what happens. Do you see the disulfide? Holds that piece to this piece, so it's still covalently linked. You also see here a missing couple of amino acids, and the disulfides are holding those to keep it one polypeptide. It's just there are some missing amino acids for this to be fully active. We'll get to that a little bit later. Interestingly enough, when we do plots of enzymes, what do we plot most of the time? If I asked you to do a plot, what were the things I said to plot?
Velocity over concentration.
Velocity over concentration. All right, is this velocity over concentration? What is this plot? P-nitrophenol, right? Moles per millimole of enzyme, okay, versus time. So this is different. This is going to give you a different piece of information. What is the rate of this reaction? Can you answer the question, what is the rate? Why can you not answer the question, what is the rate? Because it changes. And there is a significant sudden change, right? There's a velocity right at the beginning that is fast, represented by a much steeper line, and then one that is slower, okay, represented by the rest of the reaction. All right. In this tells us one thing. This enzyme has a burst phase, okay? There is 2 steps, at least 2 steps in this mechanism. All right? One that is quick, and then the one that is slow. The overall rate of any stepwise process is, you can't go any faster than the what? Limiting or the slowest step. So at the beginning, there's a really quick reaction, and then all of a sudden it slows down. All right, what actually happens in this particular reaction is this. The enzyme binds to the substrate, and a leaving group is given off, product. All right, that is quick. The burst phase lasts for one equivalent. That means the amount of enzyme you have and the amount of substrate, one equivalent of enzyme does the reaction really quickly, very quick, and you get lots of product, but only up to the same concentration as you had enzyme. After that, the enzyme slows down. There is a second step. The enzyme actually becomes covalently linked to the substrate. And so it attacks, part of it falls off, that's a product. But there has to be another part that falls off. But it's actually connected to it. The slow step is to release the second part. After that, the enzyme can go no faster than the release step. This is where we get to the steady state, and we can do all the kinetics about it. That front part, we can't do. That's not the steady state at that moment in time. Okay? So there's something different about chymotrypsin. We can look for burst phases in enzymes to understand there's at least 2 steps, one of which is slower. All right, so here is the enzyme. All right, a couple things that we need to understand about this. There is a substrate specificity pocket, okay? That's a fancy way to say this is kind of why we bind what we bind, okay? What is the specificity for chymotrypsin? Aromatics, big aromatics that are really hydrophobic, and that methionine, which is pretty hydrophobic. That means this pocket right here is lined with lots of hydrophobic, and it's huge to accommodate that big amino acid. If something smaller gets in there, it can't reach and make interactions, and so it might be hydrophobic, but it's too small to fit in well. But Goldilocks shaped, it is perfect for the aromatics. And this is what brings the binding of the substrate to the pocket. Okay? And so it's good for big ones that are hydrophobic. Second, there is an aspartate histidine serine. All right? This is called the catalytic triad. Okay? Normally, serines are not so reactive. Okay? But in this particular enzyme, the serine is very reactive. The way for serine to be reactive is for this to happen. This oxygen has to be deprotonated. So it becomes negative, and it can become a nucleophile. Ultimately, that's what I have to get done. To do that, this histidine is lined up perfectly to take that proton. And the histidine becomes reactive because the aspartate is in the negative ionization state, which is taking its proton. And if it took this proton, the actual histidine would become negative. And so this reacting to this and this reacting to this makes the serine reactive. Okay? The catalytic triad. Third, the oxyanion hole. Oh, good Lord have mercy. What does that mean? All right. What is an oxyanion? If I say those words, what would you do other than look up Google? There's an anion with oxygen. Okay? Not yet. You don't see an anion with oxygen, but in the middle of the mechanism, there will become a negatively charged oxygen, which is the transition state, which is the high energy state. That right there, those side chains, will stabilize that or make an interaction temporarily to lower that energy barrier. Okay? All right. Now, here's where the artist gets really wound up. All right. Substrate. There's the aromatic. There's the aromatic. Here's the carbon. That's the carbon. Here is the carbonyl. There's the carbonyl. Here's the bond to the nitrogen. And that is the bond to nitrogen. Okay? Also, this bond to oxygen here is kind of long too. Okay? Three-dimensional structure on a flat sheet of paper. Okay? So the orientation is not optimal. All right? Let's see what happens. Oh my goodness. There's arrows. This makes my heart a little flutter. Okay? The organic is coming back. Okay, so watch this. Number one, I formally take the proton off of the oxygen on the serine. The serine becomes transiently negative and attacks the carbonyl. Why would it attack the carbonyl? When the oxygen is negative, it wants to do what? Attack the carbon. But why the carbon? Because it's what? Partially positive. Because why?
Because
the oxygen on the carbonyl
is partially negative
because of electronegativity. All right. Now, here is 2A and 2B, and here is 2. If you write it in organic chemistry, you may actually show the negative charge sitting there on the oxygen, and then the negative charge attacking that carbonyl. Actually, in an organic flask, that is the way to actually write it. The oxygen has to have that negative charge sitting around on it for a little while, and it's got to go find its substrate to attack. In biochemistry, I say that bond attacks immediately. That is true within the biological system because they are optimized and right next to each other, and the attacking happen almost simultaneously. Besides, it's a lazier way to do it. Biochemistry lazy. Okay. When I attack the carbon, I now form 5 bonds to carbon. If ever you wrote 5 bonds to carbon on CHEM-321, what do you get? A big red box, right? Man, it gives you a huge red box, right? And then when you get it right, it gets you this little tiny, the smallest font green, correct? But it gives you a big red box. All right. When you attack, you have to go through a transition state. If you attack something that has a double bond, the electrons have to kick up onto an intermediate. And when that oxygen in step number 3 gets onto the negative charge gets on the oxygen, that's okay because it's in the what? The oxyanion hole. And it's in a transition state. Okay, so I'm here now in the transition state down here. All right, it's stabilized, but it's not stable. Okay, it's lower in energy, it's still the high energy state. So what really wants to happen is it wants to go back. And so one, it will kick back down. And then I form a double bond back to carbon, but now I have 5 bonds to carbon, something has to leave. And lo and behold, that histidine now has an extra proton on it. And so this bond, number 2, that was bound between the carbon here and the nitrogen here, is broken, and this electron picks up that proton, and the rest of the peptide floats away, and that becomes the new N-terminus for part of the protein. I have broken the bond. That's the function of the protease. But at this point in time, the enzyme is dead because the serine is actually attached to the other half of the protein. To regenerate it, okay, so I just did this one. I just kicked it down. This kicked off, picked up the proton. The electrons go back onto the nitrogen. What has to happen is water needs to get into the mix. Okay? Water can come in here. The nitrogen, and the artist didn't do this well. The nitrogen will take that proton. Then this, I would actually say, that pair of electrons will attack. I kick up, create another oxyanion, and almost done. The oxyanion will be temporary. It'll kick back down, and now this will kick and pick up that proton, and the other half of the peptide floats away. And I'm back to its original, and it can now go hit another piece of peptide, and it will break down every bond on the carboxy side that is aromatic or bulky hydrophobic. Okay, and I'm back to the original state. There are a number of serine proteases that use the catalytic triad, oxyanion hole, and a substrate specificity pocket, and their mechanisms work exactly the same way. Chymotrypsin, elastase, and trypsin contain about 40% overall sequence identity, the exact same amino acids in the exact same places. If you actually talk about the internal ones, 60% of the amino acids, the exact same place, the exact same amino acid. The thought about how all 3 of these have come about is that one was optimized, and through evolutionary changes, you would change the specificity pocket, and you would build much more effective degradation of proteins. If by chance you change the catalytic triad, that would be selected against because it didn't give you any benefit. And so there's a thought or a terminology that this is a divergent evolution from one common gene. There are a whole class of other serine proteases that do have the catalytic triad, that have absolutely no sequence identity. That would be a development of a gene that would become to what they call a convergent evolutionary process. To break a peptide bond under pH of 7 very quickly in an aqueous solution, there's only so many ways to do that, and over trial and error, having a catalytic triad is the best that has been seen, and so it came to the same conclusion, but from a different pathway. Do you remember chemistry that we used to break peptide bonds? It was all way back in last chapter's test. Yeah, we did hydrolysis for the amino acid compositions. What did we have to do? We took a sample. How long did it take? What conditions did we have to have? 6 molar hydrochloric acid. You bi-concentrated at 12. Okay? So this is 6 molar for 24 hours at 110 degrees. Okay? That's over boiling water. We're at 37 degrees pH 7, and we're making peptide bonds. The body is a lot more efficient. Now, what I see is a wonderful design. The difference between trypsin and elastase. The chymotrypsin has a big hole that accommodates hydrophobic. Trypsin binds to positively charged amino acids, lysine, arginine. It's got a very big hole, and look what lines it. Aspartate. What do we know about aspartate? Normally its charge is what? Negative. What I want you to understand in terms of each amino acid is going back to which category it was, or you could have looked back at the last slide and saw that aspartate was part of the catalytic triad and was negative. Okay? And so that's where the specificity comes in. Elastase will break on the carboxy side of small nonpolars. And so there's not a lot of room, but it is hydrophobic, so it has to be small nonpolars. Trypsin breaks on the carboxy side of arginine and lysine. And so if you have a combination of all of these and you have proteins, they'll chop them all up. Okay? Interesting enough. How do you stop this thing? Well, once you're done with your steak, and every peptide in the steak is broken up, what does it do? Finds any other protein in there. So a chymotrypsin can attack another chymotrypsin, or a chymotrypsin can attack a trypsin, and they digest themselves at the end of the reaction. We're going to get a place that these are going to be turned on. The only way to turn them off is destroy them, but it's part of the digestive process. Here's the whole convergent evolutionary process versus the divergent, which was much more interesting a couple years ago when we had the divergent series. All right. So you've now learned 3 enzymes. Number 4, enolase. Enolase, substrate, 2-phosphoglycerate, product, phosphoenol pyruvate. You may see this one as PEP a lot of times. Can anybody tell me where you find that other than the body? I got that. You may or may not know yet, but you will know. Man, you guys are just lively. Part of the glycolysis pathway. All right. The enzyme is called enolase. This one is less helpful in the name. Most enzymes are pretty helpful in what is going on with the name. Either they'll name the substrate or the product and tell you a little bit of what's happening. ACE breaking down doesn't really help you much in this case. It comes from the fact of an intermediate that will form. This is an older name, not the technical name, but enolase is used much more often than not. Okay. Oh, good. Catalyzes a step in glycolysis. I'm glad I put the answer on there right for you. All right. Uses a cofactor. The other enzyme did not use a cofactor. This will. Okay. Facilitates dehydration. Okay. Dehydration. The loss of water. Okay. Now, ultimately, one of the very, very first reactions you learned in organic chemistry was this. And it looked probably like this in the textbook. If you actually looked at the textbook. I don't know how it was taught. Well, it probably looks kind of like this on a computer projected. So that's familiar. Okay. Now, I'm not going to take that. I'm not just going to say base. In organic chemistry, you actually learned that this can be catalyzed through a base reaction. Base catalyzed. And it can also facilitate through a acid catalyzed, but we're going to do the base catalyzed here. And in this base catalyzed reaction, I will deprotonate the proton. I will, oops, if I could draw, I will form a double bond, and the leaving group will be hydroxide. And it won't be converted into water as a leaving group until you work up the pH, but effectively, you've taken a proton and you've left out a hydroxide. You can see the water formation here and then a regeneration of a hydroxide here. All right, so if I take a look at this reaction, doesn't matter. In the one that you learned in the textbook, they had blanks or they had R groups. Here, what's going to kill you is this. You're going to see lots and lots of R groups that really don't matter. But if you identify what's actually happening, inventory is very important. All right, up here, up there, perfectly the same. Here, here, perfectly the same. Nothing happened. Here, I have a hydroxide. Here, I don't. Here, I have no proton. Here, I do. Everything else goes away, and I focus on that and this. And so I might write some sort of base, and you may predict this. And I can pick up a proton, okay, to water falling off. And there's the water produced. That could be a wonderful guess at what's going on, but I'm going to show you what really happens. Okay, it's going to be similar to this. But what did I say is a cofactor in this? Magnesium, okay? That's one thing. Also, organically, this proton needs to be acidic. Protons are usually acidic if they sit next to a carbonyl. Is this sitting next to a carbonyl? Be very careful. No, it's sitting next to an acid. Acids are not, a proton next to an acid is not, because a proton next to a carbonyl, I can form a resonance structure. But the acid's already in a resonance structure. So it doesn't tend to make that proton that's alpha to it acidic. So in this case, what really happens is the magnesiums become part of the reaction. The magnesiums is going to, the transition state, okay, that is going to be stabilized by the magnesium is the deprotonation of the carbon, that first hydrogen that must come off. Now, instead of forming the double bond, like we thought, what's going to happen is the electrons are going to go up and be trapped in the carbon that was the acid. And that negative charge next to a negative charge is stabilized by that magnesium. Now that's the active state, that's the transition state, it is high in energy. It'll get trapped up there. A resonance form will come back to make the acid. The electrons can then form the double bond, and that hydroxide is facilitated by leaving because there's an R group to donate a proton, so that water falls off. And so the magnesiums actually lower the overall transition state where it sucks up that electron into the oxygens temporarily before the elimination occurs.